Think about this for a second. The device you're watching this on, whether it's a phone or a laptop, is an absolute marvel of speed. For decades, that speed grew at a rate that seemed, well, almost magical. But this isn't a story about magic. It's a story about brilliant engineering, hard physical limits, and the incredible cleverness that happens when you hit a wall. So let's dive into how computers got so fast, and then why they had to completely reinvent themselves.
For about 20 years, we were living in what you could call a golden age of speed. Just look at this chart. From the 80s to the early 2000s, processor performance was skyrocketing by about 52% every single year. That's not just fast, that's a genuine revolution. It meant the computer you bought was practically obsolete in a year or two. This incredible pace changed everything from our desks to the biggest supercomputers on the planet. But then look what happens. Right around the early 2000s, that beautiful, steep curve just flattens out. The race for pure, raw speed didn't just slow down, it slammed right into a wall. In fact, it hit three of them, three fundamental physical walls that changed the game forever.
So yeah, engineers basically ran headfirst into the laws of physics. They found themselves facing limits that couldn't be solved by just, making the same old thing faster. Let's break down exactly what these three massive obstacles were. First up, we have the power wall. Now, the simple way to make a chip faster is to crank up its clock speed. Think of that as its heartbeat, how many calculations it does per second. But there's a catch. Faster clocks need more power, and more power creates a ton of heat. We got to a point with chips like the Intel Pentium 4 where they were getting so incredibly hot that we were struggling to cool them with just air. We were literally approaching the point where they could melt themselves.
Okay, next up, the memory wall. This one's my favorite analogy. Imagine your processor is a Formula One race car, unbelievably fast. But your memory? It's a slow, giant cargo ship. The processor could finish its job in a nanosecond, but then it would just sit there, idling, waiting and waiting for data to arrive from that slow cargo ship. A faster engine is totally useless if you're always stuck waiting for fuel, right?
And finally, we hit what's called the instruction-level parallelism wall. For years, a big part of the speed gain came from engineers finding really clever tricks to make a single processor do multiple things at the same time within a single task. But by the 2000s, they had squeezed every last drop of performance out of that technique. All the low-hanging fruit had been picked. There just weren't any more easy wins to be found.
So, the old playbook of just make one thing faster was officially dead. It was time for a completely new way of thinking. First, let's look at how they tackled that slow cargo ship problem, the memory wall.
The solution, and this is really brilliant, is based on a key insight into how computer programs actually work. It's called the principle of locality. And it's pretty simple. It turns out that programs aren't random. They tend to ask for the same bits of data in code over and over again in a short amount of time. And that predictability, that's the secret key to solving the memory wall.
So if you can guess what data the processor is going to need next, why make it go on that long, slow trip to get it? Why not keep a copy somewhere much, much closer and faster? And that is the core idea of the memory hierarchy. Instead of going all the way to the big, slow library, that's your main memory, the CPU first checks its own personal disk, which is the super-fast L1 cache. If it's not there, it checks a nearby bookshelf, the slightly slower L2 cache. Most of the time, the data it needs is right there, completely avoiding that long, painful journey. Caches were an absolutely genius fix for the memory wall, but that still left the other two problems, the power wall and the parallelism wall. The answer required another radical shift in thinking. If you can't build one brain that's faster, why not just build a team of brains?
And this, of course, led us into the era of multi-core processors. Instead of trying to build one single massive power-guzzling core, architects started putting multiple smaller, more power-efficient cores onto a single chip. These cores could then split up the work and tackle tasks in parallel, neatly sidestepping the heat problem of the power wall and opening up a totally new way to get more performance.
What's so cool is that this pattern, hitting a fundamental limit and then completely rethinking the architecture to get around it, that's not just a CPU thing. We see this exact same principle playing out across all levels of computing.
Take data storage, for example. A single hard drive gives you two big problems. It's a bottleneck for speed, and if it fails, all your data is gone. The solution? RAID, which is basically just a team of disks working together. You can have them work together for pure speed, or you can have them mirror each other for ultimate safety. It's the same idea. A team of components is better than just one.
And a perfect modern example is network latency. Sending every bit of data to some far-off central cloud server creates a delay. I mean, you're limited by the speed of light. So what's the solution? Edge computing, which just moves the computers and the data closer to you, the user. It's the exact same principle as the memory cache we talked about, just blown up to the scale of the entire internet.
So all of these amazing solutions, caches, multi-core chips, RAID, edge computing, they're all secretly guided by one powerful underlying rule, Amdahl's law. It sounds complicated, but the idea is actually super simple. It just says that your overall speedup is always limited by the part of the system that you can't make faster. If your car is always stuck in traffic, it doesn't matter if you have a rocket engine. You have to attack the bottleneck.
This incredible cycle of hitting a wall, finding the bottleneck, and then re-architecting a clever solution has been the story of computing for half a century. And it leaves us with a really exciting question for the future. We've seen the walls of the past and the breakthroughs it inspired. So what do you think the next wall will be? And what kind of genius idea will it take for us to tear it down?